I'm Mason.
I'm Logan.
I'm Cohen.
I'm Ethan.
And this is our prototype presentation for our Solar Technologies Museum exhibit. At the start of the in-semester, we were assigned the goal of creating an interactive museum exhibit that fits the theme of the Grand Engineering Challenge of our choice. The Grand Engineering Challenges are the 14 problems deemed most important to humanity.
Our team decided on the challenge to make solar energy more economical and set out to create a more interactive museum exhibit that could educate middle school and high school age students.
For design criteria, we decided that we wanted the exhibit to be durable enough to withstand regular usage, and it needed to be cheap enough to fit within the assigned budget of $50 for new materials and $150 total. With these criteria and constraints established, we started brainstorming ideas.
The idea that we settled on creating was a light-facing, motorized solar panel that could be manipulated with a handheld flashlight. The idea fits the Grand Engineering Challenge because it enhances solar power technology to make the mechanism more efficient, and it meets the criteria of the project by providing an interactive, educational way for middle and high school age students to learn about solar.
A unique feature of the solar panel is that it is able to rotate towards the sun, or in this case, a flashlight. So the code and the servo need to line up perfectly to stay in tune with the light source. Another feature is the LED that changes color depending on how much energy is being absorbed. It ranges from the three colors, red, yellow, and green, that show none, low, and high energy, respectively. The engaging part is that people who look at our display can freely move a flashlight around the exhibit, to which the solar panel will respond accordingly. This design adds value to the original panel by giving it the ability to rotate towards the sun to get more energy instead of being just static. And it also provides an opportunity to be engaging in a museum.
This project met our original criteria to cut costs by implementing cheap or second-hand items. For example, extensive 3D printing was used in designing the prototype. In the end, the only thing we had to pay for was filament and some electrical components. We designed it to be closer to the ground than set up, meeting the criteria for easy access for all individuals in the audience to be involved. The exhibit also utilized easily replaceable and durable pieces that can withstand constant use, meeting our criteria for longevity and manageability.
The involvement of the engineering degree programs can be better represented through additional infographics and presentation materials, demonstrating to children how each component of the exhibit involves the degree programs. This met our requirements on explaining which areas of engineering were used. It appeals to our target audience with the simple display of our demonstration and their involvement, keeping kids entertained and informed in ways that anyone across all ages can understand and enjoy, creating a unique and creative educational exhibit.
To construct the model, we started with CAD. For this project, we chose to use Onshape for the easy-to-use file sharing. As pictured here, all custom parts needed to be thoroughly 3D modeled. Once all the planning had been done, we began the process of printing every part. This is where we began to have some issues, as not all the parts fit as planned or did what we needed them to. The entire assembly went through a thorough revision process, with some parts needing 10 to 15 iterations before they were functional.
The next step in construction was to test out the electronic systems. We first wired the photoresistors and the servo motor to ensure that the parts would work as we needed them to for our idea. After some minimal programming and assembling, we had a rotating panel. The early model was rough around the edges and covered in electrical tape, but it proved that the concept was feasible.
The final version of the project required us to design and print a box to contain all of the electronics. Once everything was assembled and wired together, we could begin testing.
The first criteria to confirm through testing was the functionality of the servo motor and rotating panel. Initially, the wiring struggled to withstand the mechanical motion, but after reassembling, the motor worked perfectly. The next test was to confirm that the LED matched the output of the panel. This is shown to work effectively towards our project goal.